May 17, 1943, Aberdeen Proving Ground, Maryland. Lieutenant Colonel William J. Cloyd of the Ordnance Department stood beside a massive steel shape that had arrived 3 weeks earlier aboard a Liberty ship from North Africa. The object before him was Panzer V Ausführung D. Chassis number to 10043, factory designation from Man Works in Nuremberg. In American records, it would simply be labeled Foreign Material Report number 198. The Panther tank. German propaganda had called it invincible. Field Marshal von Manstein described it as war-winning technology. Hitler himself had delayed the Kursk offensive for 2 months to ensure enough Panthers reached the Eastern Front. Now American engineers would discover whether the mythology matched reality, and what they found would shatter assumptions about German technical superiority that had dominated Allied intelligence assessments since 1940. The tank before Cloyd represented more than captured enemy equipment. It embodied a fundamental question about industrial warfare in the 20th century. Could sophisticated engineering overcome raw productive capacity? Could German technical excellence compensate for American industrial might? The answer, hidden inside the Panther's transmission housing and final drive assemblies, would prove more devastating to German military potential than any single battlefield defeat. The story of how this particular Panther reached Maryland began for months earlier in Tunisia. The German army had deployed a small number of Panthers to North Africa in a desperate attempt to counter Allied numerical superiority. Most broke down before seeing combat. This one, belonging to the Schwerpanzer Abteilung 501, suffered catastrophic transmission failure during the approach march to Kasserine Pass. The crew abandoned it intact when American forces counterattacked. Intelligence officers immediately recognized its significance. This was the first complete Panther captured by Western allies. Every component would be measured, tested, analyzed. Every design decision would be evaluated. The Reich's newest weapon would reveal its secrets under microscopes and testing rigs at America's primary armor development facility. What nobody at Aberdeen expected was just how badly those secrets would indict German tank design philosophy. The Panther project began in autumn 1941 when German forces on the Eastern Front encountered the Soviet T-34. That meeting produced genuine shock among German armor officers who had spent 2 years believing their Panzer III and Panzer for tanks represented the pinnacle of armored vehicle design. The T-34's combination of sloped armor, wide tracks for mobility, and powerful 76.2mm gun made it superior to anything in the Wehrmacht's inventory. Hitler personally ordered development of a new medium tank that could match or exceed Soviet capabilities. The contract went to 2 firms. Daimler-Benz proposed a design that closely mimicked the T-34's layout. Maschinenfabrik Augsburg-Nürnberg submitted a more conventional German design with modifications incorporating lessons from the Eastern Front. After extensive evaluation, Hitler selected the MAN design in May 1942. The decision launched a development program that would consume enormous resources while producing a tank that German industry could barely manufacture and German armies could not sustain in the field. The Panther's specifications on paper justified the enthusiasm. Combat weight of 44.8 metric tons. Frontal armor 80 mm thick at 55 degrees from vertical, providing protection equivalent to 140 mm of perpendicular plate. Side armor of 40 mm. The 7.5 cm KWK-42L70 gun could penetrate 138 mm of armor at 1,000 meters. Maximum speed of 46 km per hour. Range of 200 kilometers. These numbers impressed Allied intelligence analysts when they first appeared in reports from the Eastern Front. The reality was considerably more complex. German engineers had designed the Panther around the principle of qualitative superiority. Individual technical excellence would overcome numerical disadvantage. Each component represented sophisticated engineering pushed to performance limits. The Maybach HL-30 P30 engine produced 690 horsepower from 23 liters displacement. The transmission was an AK-7200, a complex synchromesh design with 7 forward gears and 1 reverse. The final drive used a unique double-spur gear reduction system that MAN engineers calculated would provide optimal torque multiplication while remaining compact enough to fit inside the hull. Every system prioritized performance specifications over reliability, manufacturability, or maintenance requirements. This design philosophy reflected broader assumptions within German military culture. German soldiers were better trained. German equipment was more sophisticated. German tactics were superior. Therefore, German forces needed technological advantages to offset Allied material superiority. The Panther embodied this thinking. It would be the finest medium tank in the world, and that excellence would compensate for the reality that Germany could never produce Panthers in numbers matching American Sherman or Soviet T-34 production. The first Panthers rolled off assembly lines in January 1943. Immediately, problems appeared. Early production vehicles suffered transmission failures during factory testing. Final drives broke during road marches. Engines caught fire. Suspension components fractured. MAN engineers frantically redesigned components, issuing modification orders that created version variations even within single production batches. Ausführung differed from Ausführung D in hundreds of details. Field units received tanks with incompatible parts. Supply officers struggled to maintain spare parts inventories when they could not determine which version components a particular tank required. The German Army needed Panthers desperately for Operation Citadel. The summer 1943 offensive at Kursk. Hitler insisted on deploying large numbers despite warnings from field commanders and engineers that the design remained immature. On July 5, 1943, approximately 200 Panthers attacked Soviet positions in the northern shoulder of the Kursk salient within the first day. More Panthers were disabled by mechanical breakdown than by enemy fire. By the operation's end, German forces had lost nearly all deployed Panthers, with mechanical failure causing approximately 60% of total losses. The tank that arrived at Aberdeen represented pre-Kursk production. It had never fired its gun in combat. It failed during approach march because the final drive disintegrated under normal operating loads. Now American engineers would discover why. The testing protocol Colonel Cloyd established followed standard Aberdeen procedures for evaluating foreign armor. First, complete photographic documentation of external features. Second, disassembly with measurements of every component. Third, metallurgical analysis of armor and mechanical parts. Fourth, firing tests of the main gun and secondary weapons. Fifth, mobility trials under various terrain and load conditions. The examination began with armor analysis. Engineers cut samples from the frontal glacis, turret face, and side plates. Metallurgists performed hardness tests, examined grain structure, analyzed composition. The results showed high-quality armor steel properly heat-treated and manufactured to consistent standards. The sloped frontal armor exceeded American Sherman protection significantly against the American 75mm M3 gun. The Panther's glacis plate was effectively immune at combat ranges beyond 500 meters. This confirmed what intelligence had reported. The Panther's armor protection represented genuine achievement in metallurgy and design. Where Allied tanks relied on thickness, the Panther used slope angles to maximize effective protection, while minimizing weight. German engineers had solved this problem brilliantly. The main gun testing produced similarly impressive results. The 7.5cm KWK-42 fired Panzer grenade, 3940 armor-piercing rounds with muzzle velocity of 925 meters per second at 1,000 meters range. This projectile penetrated 138 millimeters of perpendicular armor plate. The American 75mm gun on the Sherman managed only 75 millimeters penetration at the same range. The disparity was enormous. In a straight gunnery duel at typical combat ranges, a Panther could destroy a Sherman while remaining invulnerable to return fire. This explained German confidence in the design's battlefield potential, but armor protection and gun performance told only part of the story. The mechanical components would reveal truths that German propaganda carefully avoided. Disassembly of the powertrain began in early June. Engineers removed the rear hull plate to access the transmission and final drive assemblies. What they found immediately raised questions. The AK-7200 transmission was a masterpiece of precision engineering and a nightmare of practical maintenance. It required 7 different gear ratios using helical-cut synchromesh gears that allowed smooth shifting between speeds. The engineering was sophisticated. The execution revealed critical flaws. Each gear was machined to tolerances measured in hundredths of millimeters. Any deviation from specifications caused premature wear. The gears themselves were hardened through complex heat treatment, processes that required precise temperature control and quenching procedures. Examination of the captured tank's transmission gears showed surface spalling, pitting, and excessive wear despite the vehicle having traveled less than 100 kilometers. Before breakdown, metallurgical analysis revealed the cause. The gear hardening process had been performed incorrectly, probably due to wartime constraints on furnace availability or skilled labor shortages. Surface hardness measured lower than design specifications. Core hardness was inconsistent. The gears were literally wearing themselves apart under normal operating loads. This was not a design flaw. This was a manufacturing quality control failure that German industry was experiencing across all production programs by mid-1943. But the transmission problems paled beside what engineers discovered when they examined the final drive assemblies. The final drive transferred power from the transmission to the drive sprockets that moved the tracks. It represented the critical link between engine power and vehicle mobility. German engineers had designed a unique double spur gear reduction system that provided a 7-point to 5-to-1 reduction ratio in a compact package that fit inside the Panther's hull constraints. On paper, the design was elegant. In reality, it was catastrophic. The final drive housing was cast steel, relatively thin-walled to save weight. Inside, 2 sets of spur gears meshed to provide the reduction ratio. The primary gear attached directly to the transmission output shaft. It drove an intermediate gear that in turn drove the final output gear connected to the drive sprocket. Each gear was mounted on bearings pressed into the housing. Engineers at Aberdeen removed both final drive assemblies and disassembled them completely. The damage was extensive and obvious. The primary gear teeth showed severe wear patterns and stress fractures. The intermediate gear had the teeth completely broken off. The bearings showed scoring and deformation. Most tellingly, the final drive housing itself had cracked in multiple locations around the bearing mounting points. The failure mode was clear. Under the Panther's operational loads, the final drive gears generated forces that exceeded the housing's structural capacity. The thin-walled casting flexed under load, causing bearing misalignment. Misaligned bearings created uneven loading on gear teeth. Uneven loading accelerated wear and caused tooth breakage. The entire assembly was destroying itself through normal operation. Colonel Cloyd requested detailed stress analysis from the engineering division. Calculations showed that the final drive housing needed to be approximately 30% thicker to handle operational loads without excessive flexing. But increasing housing thickness meant increasing weight, which would push the Panther over its target combat weight and require suspension modifications. German engineers had optimized the design for minimum weight, accepting reliability compromises that made the vehicle effectively unusable for sustained operations. The Aberdeen team decided to conduct mobility trials. Despite knowing the final drive was already damaged, they wanted to quantify exactly how quickly the Panther's powertrain would fail under measured conditions. Replacement final drives were not available, obviously, so they would run the existing damaged units until complete failure occurred. On June 23, 1943, American test drivers started the Panther's Maybach engine for the first time on American soil. The engine ran smoothly despite having sat idle for months. German engine design and manufacturing quality remained high. The drivers engaged the transmission and carefully maneuvered the 44-ton tank onto Aberdeen's test track. The test protocol called for repeated circuits of a standardized course that included paved road, dirt road, moderate cross-country terrain, and simulated combat maneuvers involving acceleration, braking, and direction changes. Drivers would operate the vehicle until mechanical failure prevented further movement. Engineers would measure total distance traveled and document failure progression. The Panther completed approximately 150 kilometers. Before the final drive failure became catastrophic, the right final drive seized completely, freezing the right track and rendering the vehicle immobile. Disassembly showed that the intermediate gear had lost for additional teeth, and the primary gear shaft had fractured. The bearing races in the housing had deformed so severely that the gears could no longer mesh properly. 150 kilometers, 93 miles. Less than a single operational day's movement for a medium tank in mobile warfare. The Panther had destroyed its own final drive through normal operation on relatively benign terrain. In combat conditions, with emergency maneuvers, rough terrain, and sustained high-speed movement, the failure would occur even faster. The implications were staggering. German industry was producing a tank that could not reliably move from railhead to combat zone without mechanical failure. Even if it reached the battlefield intact, it would likely suffer mobility kills within days of operation. The sophisticated armor and powerful gun were mounted on a chassis that could not sustain itself mechanically. American engineers compiled their findings into Foreign Materiel Report number 198, completed in August 1943. The report's conclusions were damning. The Panther's armor and armament represented genuine technical achievements, but the powertrain design was fundamentally flawed. The final drive could not handle operational loads the transmission required. Manufacturing precision that German industry could not consistently achieve under wartime conditions. Maintenance requirements exceeded field unit capabilities. Most significantly, the report concluded that the Panther's design philosophy of optimizing individual component performance while accepting reliability compromises made it unsuitable for sustained armored warfare. A tank that broke down every 150 kilometers was not a weapon. It was a liability that consumed resources while providing minimal combat effectiveness. The report circulated through American and British intelligence agencies, reaching field commanders within weeks. It confirmed what some Allied officers had suspected from battlefield reports. German technical sophistication was producing over-engineered vehicles that German industry could not manufacture reliably and German armies could not maintain in field conditions. But the story of the Panther's failures went deeper than one captured tank at Aberdeen proving ground. It revealed fundamental contradictions in German military-industrial strategy that would doom the Reich's ability to sustain armored warfare. Before we continue examining how this technical failure reflected Germany's broader industrial crisis, I want to take a moment to thank you for watching. This channel exists because of viewers like you who value deep historical analysis over surface-level content. If you're finding this examination of the Panther's mechanical failures as fascinating as I do, please consider subscribing and hitting the notification bell. These long-form historical investigations take extensive research and fact-checking to ensure accuracy. Your support through subscriptions, likes, and comments helps me continue producing content that treats history with the seriousness it deserves. Now, let's return to 1943 and discover how the Panther's final drive problems revealed something far more troubling about Germany's ability to wage industrial warfare. The Panther's mechanical inadequacies were not secrets to German military leadership. Field reports from the Eastern Front after Kursk painted a devastating picture of operational readiness. Panzer Regiment 39, equipped with 96 Panthers for Operation Citadel, reported only 43 vehicles operational by July 10th, just 5 days into the offensive. Of the 53 non-operational tanks, 31 had suffered final drive or transmission failures, 12 had engine fires. Only 10 were disabled by enemy action. General Heinz Guderian, Inspector General of Panzer Troops, received these reports with growing alarm. Guderian had opposed rushing the Panther into combat before mechanical problems were resolved. He understood that introducing an unreliable weapon damaged not just immediate combat effectiveness, but long-term industrial capacity by consuming spare parts and maintenance resources that could support proven designs like the Panzer IV. In September 1943, Guderian submitted a detailed memorandum to Hitler outlining the Panther's technical failures and requesting either a complete redesign of the final drive and transmission or a return to increased Panzer for production. Hitler rejected both suggestions. The Panther would continue in production. Engineers would fix problems incrementally through running modifications. Germany needed the Panther's superior armor and firepower to offset Allied numerical advantages. This decision reflected Hitler's fundamental misunderstanding of industrial warfare. He believed that individual weapon quality could compensate for quantitative inferiority. If a single Panther could destroy 3 Shermans, then producing 1/3 as many Panthers as America produced Shermans would achieve parity. The mathematics seemed logical. The reality was more complex. American Sherman production in 1943 totaled approximately 21,000 tanks. German Panther production in the same year reached 1,848 vehicles. The actual production ratio was not 3-1, but more than 11-1. Even if each Panther could reliably destroy 11 Shermans before being knocked out, which battlefield results never approached, the numerical disparity remained insurmountable. But the comparison was worse than simple numbers suggested. Those 21,000 Shermans could move from factory to battlefield and operate for thousands of kilometers with routine maintenance. The 1,848 Panthers required constant mechanical intervention, consumed enormous spare parts inventories, and frequently broke down before reaching combat zones. Effective combat power depended not just on vehicles produced, but on vehicles operationally available at the critical point. American armored divisions in Europe typically maintained operational readiness rates of 75 to 85%. German Panther units rarely exceeded 50% operational readiness and often dropped below 30% during active operations. A German Panther battalion authorized 76 tanks might field 38 operational vehicles. An American Sherman battalion with 77 authorized tanks would field 65 to 70 operational vehicles. The mathematics of attrition warfare became brutally simple. Even if Panthers achieved favorable kill ratios in individual engagements, which they often did due to superior armor and firepower, they could not replace losses. American industry produced Shermans faster than German guns could destroy them. German industry could not produce Panthers fast enough to replace combat losses, let alone mechanical failures. The Aberdeen Proving Ground tests revealed another critical factor that battlefield statistics alone could not show. The Panther's maintenance requirements exceeded German field unit capabilities. American engineers documented that replacing a Panther final drive required removing the rear hull plate, disconnecting the transmission, extracting the entire final drive assembly, installing the replacement, reconnecting all systems, and testing operation. The procedure demanded approximately 16 man-hours under ideal shop conditions with proper tools and spare parts available. In field conditions, without overhead cranes, with limited tools, and under potential enemy fire, the same repair could take days. German maintenance companies were chronically undermanned and lacked specialized equipment. Spare parts shortages meant that even when mechanics diagnosed problems, they often could not obtain replacement components. Panthers sat immobilized awaiting parts while American Shermans continued operating. The contrast in maintenance philosophy was striking. American engineers designed the Sherman for field maintainability. The Continental R975 engine could be removed and replaced as a complete unit, using a simple hoiston approximately 4 hours. Transmission replacement required similar time. Track replacement was straightforward. Most repairs could be accomplished by battalion maintenance sections. Without specialized factory tools, German engineers designed the Panther for maximum performance. Maintenance was a secondary consideration. The assumption was that Germany's superior technical training and industrial infrastructure would handle whatever maintenance requirements emerged. By 1943, that assumption was obsolete. German maintenance infrastructure was collapsing under the combined pressures of Allied bombing, resource shortages, and the simple reality of fighting on multiple fronts while outnumbered. The metallurgical analysis that Aberdeen engineers performed on Panther components revealed another dimension of German industrial decline. Early war German armor showed consistent high-quality steel with proper alloy composition and heat treatment. The captured Panther's components showed significant variations in quality. Some parts met specifications, others showed alloy shortages, improper heat treatment, or manufacturing defects that indicated quality control failures. Germany faced critical shortages of molybdenum, nickel, and other alloying elements essential for high-quality armor steel. As the war progressed, these shortages intensified. Metallurgists compensated by adjusting heat treatment processes and using substitute alloys. But these modifications compromised material properties. Armor that should have been homogeneous showed inconsistent hardness. Gears that required precise hardening showed core structures indicating rushed or improper processing. The labor situation compounded material problems. German industry increasingly relied on forced labor. From occupied territories and concentration camps, these workers had no incentive to maintain quality and often engaged in deliberate sabotage. Skilled German workers were being drafted into military service, further eroding manufacturing expertise. The combination of material shortages, inadequate labor, and Allied bombing created industrial conditions where even excellent designs could not be manufactured to specifications. American intelligence analysts studying the Aberdeen report recognized that the Panther's failures reflected Germany's broader industrial crisis. German engineering remained sophisticated. German designers could create impressive weapons, but German industry could no longer reliably manufacture those weapons to design specifications or produce them in adequate quantities. The gap between design excellence and manufacturing reality was widening. British intelligence reached similar conclusions from examining Panthers captured in Normandy after D-Day. In July 1944, the School of Tank Technology at Chertsey received a Panther Ausführung G captured near Caen. British engineers conducted tests parallel to Aberdeen's earlier work. Their findings confirmed the final drive problems and added new concerns about armor quality degradation in late production vehicles. The Chertsey report noted that the Ausführung G's armor, while still formidable, showed more manufacturing defects than earlier production models. Welds were less consistent. Plate thickness varied more than specifications allowed. Heat treatment appeared rushed. The conclusions supported intelligence assessments that German armor quality was declining as the war continued. Combat reports from Normandy provided real-world validation of the mechanical problems Aberdeen had documented. The 2nd Panzer Division deployed 127 Panthers to Normandy in June 1944. Within 3 weeks, 72 were total losses. Of these, 41 were mechanical breakdowns that crews abandoned during the retreat after the Allied breakout. Only 31 were knocked out by enemy fire. The Panzer Lehr Division told a similar story. 95 Panthers deployed in June. By August, the division had lost 76 Panthers. Unit records showed that final drive and transmission failures accounted for approximately half the losses. The division's maintenance companies could not keep pace with mechanical breakdowns. Even before intense combat operations began, German commanders adapted tactics to accommodate the Panthers' mechanical limitations. Panthers were held in reserve, when possible, brought forward only for critical battles, then withdrawn quickly to minimize road march distances. This preserved mechanical reliability, but sacrificed the sustained armored operations that Panzer doctrine emphasized. The Panther became a defensive weapon, positioned in prepared positions where its superior armor and firepower could ambush Allied armor rather than the mobile offensive weapon German doctrine required. But even in defensive roles, the final drive problem created vulnerabilities. Once positioned, Panthers could not rapidly relocate if tactical situations changed. Crews knew that moving their vehicles risked mechanical breakdown that would leave them immobilized in the open. The psychological factor reduced tactical flexibility and made commanders reluctant to maneuver, even when operational necessity demanded it. The Aberdeen engineer's most damning conclusion appeared on page 47 of Foreign Material. Report 198. After detailed analysis of every system, they wrote, "The Panther tank represents a remarkable achievement in armor protection, and armament mounted on a fundamentally unreliable chassis. Current design of the final drive and transmission makes the vehicle unsuitable for sustained armored operations. Unless these components are completely redesigned, the Panther will remain a maintenance liability that consumes resources disproportionate to its combat effectiveness." The report recommended that American tank design efforts focus on reliability and maintainability, rather than pursuing maximum performance specifications. The Sherman's proven mechanical reliability represented better military value than hypothetical, superior performance that could not be sustained in field conditions. This recommendation influenced American armor development for the remainder of the war. German attempts to fix the Panther's mechanical problems continued throughout the war. MAN engineers redesigned the final drive multiple times. Ausführung introduced strengthened housings. Ausführung G incorporated revised gear ratios. Late production Panthers received improved bearing designs and modified lubrication systems. Each modification helped marginally, but none solved the fundamental problem that the design optimized performance over reliability. The final drive continued failing. Average distance between major mechanical failures improved from 150 kilometers in early models to perhaps 400 kilometers in late production. But this remained inadequate for armored warfare requirements. American Sherman final drives routinely lasted for over 2,000 kilometers. Soviet T-34 final drives, while less sophisticated than either German or American designs, proved remarkably durable in field conditions. By 1944, German industrial planning faced impossible choices: continue Panther production despite mechanical problems, or shift resources to simpler designs that industry could reliably manufacture. Hitler insisted on continued Panther production, believing that technical superiority would eventually overcome production limitations. This decision locked Germany into manufacturing a weapon that consumed disproportionate resources, while providing combat effectiveness. Limited by chronic mechanical unreliability, the resource allocation consequences were severe. Each Panther required approximately 300,000 man-hours to manufacture, compared to 55,000 man-hours for a Sherman. The specialized machining for the transmission and final drive components consumed machine tool capacity that could have produced simpler, more reliable components for multiple vehicles. The alloy steel requirements for a single Panther could produce armor for 3 Panzer IVs or 5 Stug assault guns. German commanders in the field increasingly questioned whether the Panther's tactical advantages justified its logistical costs. General Hermann Balck, one of Germany's most successful Panzer commanders, wrote in his post-war memoirs that he preferred Stug assault guns to Panthers for most missions. The Stug was mechanically reliable, easier to maintain, cheaper to produce, and while lacking the Panther's mobility and turret, provided adequate firepower for defensive operations that characterized German armored warfare. After 1940-3. If you've stayed with me this far through this deep examination of the Panther's mechanical failures, you're exactly the kind of viewer this channel serves. History isn't just about grand strategies and famous battles. It's about understanding the technical realities that determined outcomes. The Panther's final drive failure after just 150 kilometers tells us more about why Germany lost World War II than a dozen accounts of individual battles. If this kind of detailed historical analysis interests you, please take a moment to like this video and share it with others who appreciate serious historical content. The algorithm rewards engagement, and your support helps ensure that deeply researched videos like this one continue to reach audiences who value historical accuracy over entertainment. Now, let's examine how the Panther's failures influenced post-war tank design, and what lessons military planners drew from this expensive German mistake. The story of the Panther's mechanical failures did not end with Germany's defeat in 1945. The lessons learned from Aberdeen's testing and from battlefield experience influenced armored vehicle design for decades afterward. American, British, and Soviet tank designers all studied the Panther carefully, adopting some features while deliberately rejecting others. The Panther's sloped armor became standard on post-war tank designs. The American M46 pattern, developed immediately after the war, featured sloped frontal armor directly inspired by German design principles. Soviet post-war tanks from the T-44 through the T-54 series incorporated increasingly sophisticated armor slope angles. British tank designers, traditionally conservative about armor configurations, gradually adopted slope designs in post-war vehicles. But no major power adopted the Panther's approach to final drive design, the lesson that Aberdeen's engineers documented, that optimizing component performance while accepting reliability compromises was strategically counterproductive, became fundamental to post-war armored vehicle development. Reliability, maintainability, and producibility were recognized as combat multipliers equal in importance to armor protection and firepower. The American M48 and M60 series tanks that served through the Cold War embodied this philosophy. Their final drives used robust designs with safety margins that accepted slight performance penalties to ensure mechanical reliability. Transmission systems emphasized durability over maximum efficiency. Engine compartments were designed for rapid power pack replacement in field conditions. The entire design philosophy prioritized sustained operational readiness over maximum performance specifications. Soviet tank design followed similar principles. The T-54 and T-55 series used simple, robust mechanical components that could be manufactured with loose tolerances and repaired by minimally trained crews. Performance specifications were modest compared to what Soviet engineers could theoretically achieve, but reliability was exceptional. A T-54 could operate for thousands of kilometers with minimal maintenance, exactly what the Panther could never accomplish. German engineers who survived the war and later worked in Western tank development brought sophisticated technical knowledge but also hard-learned lessons about the limits of technical sophistication. Post-war German tank projects, when the Bundeswehr was re-established, emphasized reliability and maintainability rather than pursuing maximum performance. The Leopard 1, developed in the 1960s, represented a balanced design that incorporated German engineering expertise without the fatal flaws that characterized wartime vehicles. The Panther's influence on post-war military thinking extended beyond pure technical lessons. The vehicle became a cautionary example of how industrial strategy and weapon design must align with manufacturing capabilities and logistical realities. Military planners recognized that fielding weapon systems that maintenance infrastructure could not support was strategically counterproductive. Regardless of their theoretical performance advantages, American military doctrine developed during the 1950s explicitly incorporated these lessons. The Pentamek reorganization and subsequent road restructuring emphasized sustainability of combat power through reliable equipment and robust logistics. Tank designs were evaluated not just on gun performance and armor protection, but on operational readiness rates, maintenance requirements, and spare parts consumption. The Panther's failures had taught that availability was a weapon characteristic as important as any performance specification. For historians and military analysts, the Panther tank represents a perfect case study in the relationship between technical excellence and strategic effectiveness. The vehicle's design showed that German engineers remained capable of sophisticated work throughout the war. The gun was genuinely superior to Allied tank armament. The armor protection was excellent. The mobility, when the vehicle actually ran, was adequate for tactical requirements. But these technical achievements were mounted on mechanical systems that German industry could not reliably produce and German armies could not adequately maintain. The result was a weapon that absorbed enormous resources while providing combat effectiveness limited by chronic unreliability. In the calculus of industrial warfare, this made the Panther a strategic failure despite its tactical potential. The Aberdeen Proving Ground tests of May through August 1943 revealed these truths with brutal clarity: 150 kilometers to catastrophic final drive failure, transmission gears wearing out under normal loads, manufacturing quality control failures evident in every major component. The detailed technical analysis showed that Germany was losing the industrial war, even as individual German weapons retained technical sophistication. Lieutenant Colonel Cloyd's final report to the Ordnance Department concluded with an observation that captured the strategic implications. The Panther tank demonstrates that technical excellence in design cannot compensate for inadequacies in manufacturing capability and logistical support. American armored forces should continue emphasizing mechanical reliability, ease of maintenance, and volume production. These characteristics provide greater combat power than pursuit of maximum performance, specifications that cannot be sustained in field conditions. This conclusion, based on careful examination of a single captured tank, proved prophetic. As the war continued, German armored forces increasingly struggled with mechanical reliability problems across all vehicle types. The Tiger heavy tank suffered similar final drive issues, though less severe than the Panther. Even the long-serving Panzer IV experienced quality control problems. As manufacturing standards declined, German armored effectiveness degraded not primarily through combat losses, but through mechanical attrition that maintenance infrastructure could not overcome. Allied forces, meanwhile, maintained high operational readiness rates through emphasis on reliability and maintainability. Sherman tanks continued operating. Spare parts remained available. Maintenance procedures were straightforward enough that field units could execute them. The unglamorous characteristics that made the Sherman less impressive than the Panther, in direct comparison, proved decisive in sustained operations. The human cost of the Panther's mechanical failures was significant, though difficult to quantify precisely. German tank crews abandoned numerous Panthers during retreats, when mechanical breakdowns left vehicles immobilized. These crews often could not reach friendly lines and were killed or captured. The psychological stress of operating vehicles known to be mechanically unreliable affected crew performance and morale. Maintenance personnel exhausted themselves attempting repairs that inadequate spare parts inventories made impossible. For German industry, the Panther program represented enormous resource consumption for inadequate return. The specialized manufacturing required for Panther production absorbed machine tool capacity, skilled labor, and critical materials that could have produced larger numbers of simpler vehicles. Economic historians have calculated that Germany could have produced approximately 3 Panzer IVs or Verstug assault guns for the same resource expenditure as one Panther. Given the Panther's reliability problems, this alternative allocation would likely have provided greater combat effectiveness, but Hitler's insistence on technical superiority made rational resource allocation impossible. The Panther continued in production until the war's end, consuming resources desperately needed elsewhere while providing combat forces with a weapon they could not reliably employ. The final production figures told the story. Germany manufactured approximately 6,000 Panthers between January 1943 and April 1945. America produced over 49,000 Shermans in the same period. The Soviet Union built over 31,000 T-34s, even accounting for the Panther's theoretical superiority in direct combat. The numerical disparity was insurmountable, and that theoretical superiority was undermined by mechanical unreliability that kept Panthers in maintenance shops rather than on battlefields. German armored forces faced Allied tanks that could move, fight, and continue operating while their own vehicles broke down from normal use. The captured Panther that revealed these problems. 2 American engineers remained at Aberdeen Proving Ground. After testing concluded, it became a permanent exhibit, a teaching tool for armored vehicle designers and a reminder of the lessons learned. Engineers training for armor development were required to study Foreign Material Report 198 and examine the actual vehicle. The message was clear: reliability matters more than performance specifications that cannot be sustained. Post-war technical manuals reference the Panther's final drive failure as an example of poor design. Practice engineering textbooks on armored vehicle development included case studies analyzing what went wrong and why. The Panther became famous not for its intended role as a war-winning weapon, but as a cautionary tale about the consequences of divorcing technical ambition from industrial reality. For the German tank crews who operated Panthers during the war, post-war accounts consistently emphasized frustration with mechanical unreliability. Veterans described the experience of watching their vehicles break down during crucial operations, of abandoning perfectly good guns and armor because the final drive failed, of knowing that their chances of surviving depended on a transmission that might break at any moment. The Panther's technical sophistication provided no comfort when it left crews stranded in enemy territory. Soviet forces captured large numbers of Panthers during the advance into Germany. Some were evaluated by Soviet engineers, most were scrapped, considered too unreliable and maintenance-intensive for Red Army use. The Soviets drew their own lessons from examining German armor, focusing on the value of simple, robust designs that conscript armies could maintain and socialist industry could mass-produce. The T-54 embodied these principles, becoming perhaps the most successful tank design in history, with over 95,000 produced, and service spanning 7 decades. The technical analysis that began when a single captured Panther arrived at Aberdeen proving ground in May 1943 ultimately influenced military thinking far beyond immediate wartime applications. The vehicle became a symbol of a particular approach to military technology, one that prioritized individual excellence over systematic effectiveness. The failure of that approach, documented in careful engineering tests and confirmed by battlefield experience, shaped how democratic industrial powers thought about weapon development for generations. The Panther tank remains one of World War II's most recognizable armored vehicles, featured prominently in histories, museums, and popular culture. Its distinctive profile and reputation for powerful armament ensure continued fascination. But the real significance lies not in the mythology of German technical superiority, but in the mundane reality of a final drive that failed after 150 kilometers. That failure revealed truths about industrial warfare that determined the war's outcome more surely than any individual battle. The story of the Panther's mechanical failures reminds us that history's most important lessons often hide in technical details that don't make exciting headlines. A final drive breaking after 93 miles tells us more about World War II's outcome than dramatic accounts of tank battles. Understanding these details requires the kind of deep research and careful analysis that this channel is committed to providing. If you've made it to the end of this examination, you're clearly someone who appreciates history presented with accuracy and depth. Please subscribe, enable notifications, and consider supporting this channel through likes and comments. Every bit of engagement helps ensure that serious historical content continues to reach audiences who value truth over entertainment. Thank you for watching, and I'll see you in the next deep dive into the technical realities that shaped history.